My name is Dean Crowley, student number is 19100-583, and I'll be making this presentation on the structure of 3D scaffolds today. So for this experiment we used FDM, or fused deposition modelling, to produce our scaffold with PLA Scaffold biomaterial, which is one of the best synthetic polymers on the market today. We will be examining the porosity of the scaffolds, which is important because the body's natural ability to regenerate needs to be able to regenerate into the pores, and this depends on the size and quantity of pores available when producing the scaffold. Our hypothesis for this is that the PLA log scaffold is sufficient for use in bone tissue as opposed to solid scaffold. In this slide we see the results of the comprehensive modulus, and shows what the results of the Zwick tester. 4 solid and 4 log pile samples were loaded under compression, and about 1.5 strain, 900 newtons was reached. Using this data we can find the secant modulus and the comprehensive modulus. Our null hypothesis for this instance states that the log piles are not statistically different from the solid modulus. As can be seen in figure 3, the comprehensive modulus for the solid scaffold is 377.8 megapascals, and the log scaffold is 194 megapascals. Using a p-value of greater than 0.01, the rejecting null hypothesis include that porosities of the scaffolds are statistically different. Degradation can be seen with 3 samples of each. The mass is measured before degradation, after 3 days of degradation, 7 days of degradation. As seen in figure 4, by day 3 the log pile scaffolds had an average degradation rate of 15%, solid scaffold had degradation rate of 10%. By day 7 the log pile scaffold average degradation rate was down to 9%, and solid scaffold was down to 7%. We proposed 2 null hypotheses that there would not be significant difference within each scaffold, and those taken on the 7th day and 3rd day, and obviously significant difference between readings taken from the different scaffolds. Based on our calculations, the first null hypothesis is rejected for log pile scaffolds and not rejected for solid scaffolds. Second null hypothesis is not rejected for day 3s between different scaffold types, and is rejected between the 7s between different scaffold types. In porosity, as seen in figure 6, there is an average of 0.479 and 0.501 taken. Our null hypothesis states that the porosity in non-degraded and degraded scaffolds is not statistically different. Based on a one-tailed t-test, we get a value of 3.55 with 10 to minus 5 for p. Therefore, we reject the null hypothesis. The porosity is significantly different between the degraded and non-degraded log pile scaffolds. In conclusion, our comprehensive modulus using a relative density of 52%, the modulus is strut material. The theoretical value for the open cell modulus is calculated to be 102 megapascals with constant C1 as per Gibson and Ashby literature. Theoretical prediction is 92, which is less than the experimental result, primarily due to density, along with the outlier that was mentioned earlier. Degradation assumptions, we noted that the degradation rates between day 3 and have a large standard deviation due to an outlier which degraded much less than the others by day 3, but by day 7 was more uniform, and with the others. This would have affected the mean degradation rate, which could account for the difference in statistical significance between day 3 measurements in a log pile scaffold and those in solid scaffold, and the statistical difference between day 7 measurements in the log pile scaffold and those in solid scaffold. Porosity results make sense because as the scaffold degrades, struts break down. As a result, the solid volume decreases relative to the overall scaffold volume, leading to a decrease in density and increase in porosity. In conclusion, we ultimately believe that PLA log scaffold will be suitable for use in bone tissue strategy. Based on these experiments, it has a high comprehensive modulus and a low degradation rate.